Hi, I'm Nirmal Malapaka. I'm a kernel developer here at Wolfram Research, and my talk today is about complex valued visualizations in the Wolfram language. Hello, everyone. I work in the visualization team, and today I'm going to be talking about complex valued visualization in the Wolfram language. So in version 10, we introduced two famous complex plots, Julia set plot and the Mandelbrot set plot. And in this version, we are going to release a set of 5 plots, which will help you visualize complex numbers and complex functions in 2D and 3D. So these are built on top of our existing visualization functions. And some of them are convenience functions, but all of them are very useful and handy. So we have ReImPlot, AbsArgPlot, and then we have 3 plots on the complex plane. So in this talk, I will walk you through what these plots do, and then we'll take a look at a couple of examples. So first up is ReImPlot, and this one takes a function and plots both the imaginary part as well as the real part of the function. So whereas plot, for example, of a function like square root of x will just give you the real part. ReImPlot will give you both the imaginary and the real parts. And it'll style the imaginary part slightly differently than the real part. Now for a simple example like this, you can of course do it with plot. Just split the real and imaginary parts and plot them. But if you have multiple functions, and especially if you have overlap between the real and imaginary parts, it's going to be somewhat tricky to keep the styles straight. And so that's why having a function like this would be handy. And we also optimize the different options for these plots. So for example, you get a special value for plot legends and a couple of new options like ReIm style and ReIm labels, which split the labels for the real and imaginary parts. So you get a nice plot. Next one is AbsArgPlot, and this one will plot the absolute value of the function and color it by the value of its argument. So if you look at the plot of the absolute value of this function, you'll see that it matches the shape that you get for AbsArgPlot. And then what it does is it takes the argument values of the function. So you can see that in this case, you only have 2 values. It's a step function. And then it'll map those values to the color scheme, which comes from the color function. And then it will match up the values. So you can see here that on the left, for the negative x-axis, you see that sort of mustard color, which matches up on the legend with pi over 2. And on the right, you get the emerald, which matches up with 0. So the same thing is illustrated here with a plot of the argument of the function. You can see that it's a step function. And I'm essentially doing the same thing here with color function by rescaling the value, which is the argument on the x-axis, to live between negative pi and pi, and then applying the color function to that. This, of course, is a bare bones sort of function. And yeah, it's easier to just talk about 2 colors, so that's why I picked this one. But this function really shines when you have functions that have dramatic changes in their phase. So here are a couple of examples. The bottom is a combination of sine functions, and at the top is the zeta function. And so you can see the absolute values are being plotted, and you can pick the colors, and from the colors you can infer the argument. So next up is ComplexListPlot. This is the plot corresponding to listplot on the complex plane, and it will take a list of values and plot them on the complex plane. It's easy enough to do it with listplot. Just do the real and imaginary parts of the number, and you can plot it. But again, it's convenient to have a function that plugs into the rest of the system. So if you're doing things like solving for the roots of an equation and they turn out to be complex, you can simply plug them in to ComplexPlot and plot them. And here at the bottom is another example of eigenvalues of a PDE problem. And again, you can just plug it in and make it work. That is, of course, one aspect of ComplexPlot. The other aspect is, like I said, the customization of options. So here we can do something interesting. We can just pick a sampling of complex numbers and plot them. But I'm coloring each of those points by their argument. And we can, of course, do that because color function will take argument as one of its values.
How do you do the range in the random complex? Because there's no greater or less than for imaginary numbers? Yeah, but why square? Because lots of complex numbers are not actually squared.
Complex list.
It should be a region, not just a indicator.
It indicates the left, bottom, and the top right corners.
Right. Yeah, but it should be a region.
Region for the points, list plot, or yeah, we'll get to the function part of this, but yeah. So here's another way of doing the same thing, and here I'm just doing the coloring them by the argument of the inverse of the function. So then the question becomes, can we sort of generalize this in some way where we can plot the function in the complex plane and color it by the argument? And that's what ComplexPlot does. So ComplexPlot takes a function, a complex function, and then it plots the function and colors it by the argument. The same two examples that you saw on the previous slide, here with the function, ComplexPlot of z and 1 over z. So what is the advantage of coloring a complex function this way, apart from being able to read out the argument in the color? It turns out that this kind of coloring scheme will help you identify zeros, poles, and essential singularities on the function. So if we take the first function, the first plot here, there's a 0 at the center. And if we take the color scheme, the endpoints of which the start and end points are red and violet. And so the colors change in a counterclockwise direction, starting from red, going all the way to violet. And that's how you can identify that there is a 0 there. And when you have a pole, the orientation of the change of colors flips, and now the colors change from red in a clockwise direction to violet. Apart from being able to tell if there are zeros or poles, we can also tell how many of these zeros and poles we have. And so here is an example with 3 plots. And the first one has 2, the second one has 3, and the third one has 4 poles. And so the colors cycle multiple times. So the first example with 2 poles, the 2 zeros, sorry, the colors go from red to violet, and again from red to violet twice. This should be fairly obvious why that is the case, but it's still sort of fun to look at it on a manipulate. So here's an example with 4 poles, 4 zeros, and if we pull the zeros apart, you can see that each one of those zeros has the color cycle associated with it. So you have the red going to violet. So when there is this coincidence of these zeros, you get that color cycle. For essential singularities, the pattern is slightly different. And so you have the colors in this case going, you have this sort of ring pattern for the colors, and the colors change along the diagonal from left bottom to the top right, and it goes from red to violet this way. So that's how we read color in ComplexPlot, but we can also add more information to this plot, and we can add the absolute value of the function to this plot, and the way we do it is by shading the plot. So we apply shading on top of the color. And the mechanism by which we do it is to use the color function. And for this plot, the color function is slightly different. It's a list, where the first element of the list is the traditional color function, and the second element is a shading scheme, which I'm going to get to in just a second. But if we turn off the color function and let the shading scheme do its automatic thing, you can see that there is a pattern being applied to the function. And if we do a 3D plot of the absolute value, you can see that that shading pattern matches the absolute value of the function. So if we put all these layers together, we get the complex plot of the function, where the function is being plotted, and it's being colored by its argument and shaded by its absolute value. And the legend shows you what exactly is happening. So there's the left part of the legend will tell you how the function is being shaded by the absolute value, and the right part will tell you how it's being colored based on the argument. So then we come to the shading scheme. So this is a snapshot from the documentation for ComplexPlot, and it lists a bunch of shading schemes we have, the named shading schemes. And I'm not going to go through the details of the shading schemes, but this table will tell you what they're attempting to do. So it turns out it's a good idea to have many of these shading schemes, because the shading scheme is trying to give you an impression of the change in the absolute value. Not all shading schemes work well with all functions. So it's good to have a few of these so you can pick the one that works best for the function that you're trying to visualize. But I'll just show you a gallery of these shading schemes applied to the function that we're discussing. And yeah, this will give you an idea of the variety of shading schemes that we have. So that is ComplexPlot. So a natural extension to this would be ComplexPlot 3D, because we get one extra dimension, so we don't have to resort to shading schemes to convey absolute value. So you can directly plot the absolute value here as the third dimension. And as you can see, the shape of the function matches the plot 3D of absolute value of the function. And the color matches the change, the phase shift of the function when compared with the plot of the arg of the function. So one thing to mention here is that the endpoints of this color scheme that are chosen by default are the same. So that's why you don't see a line along there where there is a dramatic shift here in the argument. But if you pick a color function that has distinct endpoints, then you can see that branch cut in a much more dramatic fashion. So one option that is worth a special mention here is mesh. And because mesh is slightly more useful in a 3D plot, we've taken advantage of that to assign values to mesh function. And so we can plot real, imaginary, and absolute value and argument, and we can draw mesh lines based on those values. So you can, of course, mix and match these. So I guess that's the end of my talk. I conclude with that. And yeah, sorry for using the boring function, but these plots really produce stunning visualizations, and our documentation is full of them. So if you have the conference beta, I encourage you to take a look at them. Thank you.